Hello and welcome to another exciting lecture for stats. In this lecture we will be talking about one of my favorite topics in stats, and that is nonparametric tests. So nonparametric tests are going to take what we have learned but now look at it in the inferential statistics in a nonparametric way. So up to this point, we've been using parametric tests. The z-test is a parametric test. The t-test is a parametric test. We'll actually come back to it next week and start looking at correlations and into ANOVA, and that's the f-test, and those are parametric tests as well. And these have specific requirements. The requirements for parametric tests are that you need interval or ratio level data, and they're designed to test hypotheses about a specific population parameter like the mean or the correlation. And the big thing is that these tests, all the parametric tests, and actually all nonparametric tests as well, but all statistics tests have assumptions. The parametric tests have some pretty specific assumptions that you need to meet in order to do the test. When I say assumptions, what I mean is you have specific things that need to be met in order to conduct the test. So for parametric tests, you need things like a normal population distribution. If you've got more than one population, you need homogeneity of variance. Basically, the population variances must be equal or approximately equal. So when these assumptions are met, parametric tests become the most powerful statistical tests you can do. They're almost always more powerful than non-parametric tests if the assumptions are met. That's a very key point. That is that we've got these assumptions. When they're met, we would prefer to do these parametric tests. They are better tests to do. However, if they're not met, then we can't do them. And if we do them, when the assumptions are not met, it actually causes the data to be flawed or skewed, and our stats are basically misrepresenting the data. So when the assumptions are violated, you have to go and do another test where the assumptions aren't violated. Actually, let's look on the next slide, some of the assumptions for a test. So this is a one sample t-test, the assumptions for it. Now typically you're going to see a list that's only got 3 to 4 because some of these are basically assumed as given. But that being said, these are the 5 assumptions that have to be met, even if, again, sometimes they're basically unwritten. So first is the variable needs to be interval or ratio. And basically what that means is the dependent variable, not the independent variable, but the dependent variable must be your interval or ratio level. You can't have a ordinal or nominal variable. That being said, when you're looking at, let's say, a statistical test that looked at a 1 to 7 Likert scale, you can make the argument that that's interval or ratio level, but typically that's actually just going to be ordinal. However, most people still run the parametric tests on that. And that's one thing I think that I should talk about here. And before I get back to these assumptions, that when you read journal articles and the statistics that are in journal articles in all the different science fields, what you've actually got is a lot of the time what is going on is that people are running parametric tests when they should be running non-parametric tests. Why do they do that? Well, because there isn't as much oversight. People aren't as picky about the slight, other than statisticians, people aren't as picky about using a parametric test when you probably shouldn't have, when the results aren't going to be that far off. And non-parametric tests, other than chi-square tests, which we'll get to in a minute, don't get published. So we're going to talk about two of the non-parametric tests, the Mann-Whitney U and the Wilcoxon T. And those two, doing those, you typically don't get published. The editor of the journal will ask you why you didn't use a t-test. And it's the way it is. So when I'm talking about these assumptions, just be aware that even when these assumptions are violated, many people still use parametric tests. The next is the dependent variable should be continuous. Again, even then when you've got Likert scales and stuff like that, you're going to get a variable that's not continuous and they're still running t-tests on it. Independence is important though. Independence of the observation must be independent of one another. This is a basic assumption of most statistics, so this one you usually don't see on a list because it's a basic assumption of almost all statistics. Number 4, normal distribution. So the dependent variable should be approximately normally distributed. You see 2 stars there. Let me come back to that. And then number 5 is no outliers, and that is the dependent variable should contain no outliers. Both of these have the 2 stars. You look down at the bottom and you see that a big thing that goes on here is that these 2 assumptions can be ignored using the central limit theorem. If your sample size is sufficiently large, you can assume that your sampling distribution of the mean is going to be normally distributed, and that is going to control for outliers as well. So the normal distribution and no outliers only applies to sample sizes of less than, let's say, 20 to 30. If your sample size is greater than that, then especially once your sample size gets up into 1/200 range or larger, then the central limit theorem is going to fix these assumptions. So when those conditions are not met, when the assumptions for the parametric tests are not met, we can use non-parametric tests. Now, non-parametric tests also have their own assumptions. And actually, we're only going to cover 4 non-parametric tests, 2 of them being chi-squared tests, but the 2 other ones, the Mann-Whitney U and the Wilcoxon-T, they have assumptions. And actually what's interesting is that if the assumptions for those are violated, there are other non-parametric tests that you can use. When I was an undergrad in the stats department, they had a teacher that loved non-parametric, so they actually offered a non-parametric class. So when I was an undergrad, I took a non-parametric stats class and got to see like 8 different tests you use. If this assumption's violated, you go down to this test. Now you've got assumptions there. If one of those assumptions are violated, you go to the next test. And the next test finally till you get to a test that has no assumptions. So non-parametric tests are typically designed to use with nominal or ordinal level dependent variables. And really, we're not testing about specific population parameters. However, we do look at it as almost like a median is what we're using. So we're not using the technical median, we're just using it as more of we look at parametric tests as tests on the mean, non-parametric tests as tests on the median. Again, there's either no or less stringent assumptions, and if the parametric assumptions are violated, the non-parametric tests have more power because they can be more powerful than a parametric test, because by having the parametric assumptions violated, doing a parametric test messes with the data that you have. And as it says here, if the parametric assumptions are violated, you can take an interval or ratio variable that you have and treat it as ordinal. So we're going to look at a few different tests. So here we're going to look at 4 different tests. As I said, there's a whole bunch, but we've only got 1 lecture to cover non-parametric tests, so we're going to cover the 4 biggest ones. 2 of them are ones that are actually quite common, and 2 of them are ones that are more uncommon, but they're still considered the top-end non-parametric tests. So first is nominal level variables. Anytime you have a nominal level variable, you cannot use a parametric test. It just doesn't work. How do you say that Ford or Chevy, one is greater than the other? And parametric tests require you to have the numbers in a way that one is greater than the other. So anytime you have nominal data, you cannot do parametric tests. We do the gold standard of non-parametric tests, which are chi-square tests. So you see this, the CHI square, that is chi-square. It's also written as like that. it's an X where one of the lines is more of a wave, and that's chi-square. And we're going to look at two chi-square tests. One is when you have only one variable, and that's the chi-square goodness of fit test, and the other is when you have two variables, and that's the chi-square test of independence. The goodness of fit test takes a variable that you have and looks at it and compares it to either to see if there's differences between the groups or to see if the groups meet a hypothesized distribution. And the two variable is where you're trying to see if two nominal variables are related to each other or independent from each other. Then if you've got ordinal level data, or if the assumptions are violated in interval or ratio that you knock down to ordinal level data, for these, the non-parametric tests we do, if you've got two independent samples, you do the Mann-Whitney U, and if you've got two correlated samples, two paired samples, you do the Wilcoxon matched pairs sign rank test. Yes, that's a long line. Wilcoxon matched pairs sign rank test, also called the Wilcoxon T. Then you notice that this T is capitalized. The Wilcoxon T is a different T than the student's T that we did in the previous few chapters. All right, let's start with the chi-square test. So what are chi-square tests doing? What's going on with chi-square tests? Chi-square tests are basically looking to see if your observed frequencies of a distribution. So let's say you're looking at cars and you've got Ford, Chevy, and Toyota, and you count however many go by. And you've now got observed frequencies. This goes back to our frequency distributions earlier in the semester. Your observed frequencies, how many you counted in your sample, match a hypothesized distribution, which is our expected frequencies. Whatever we hypothesize to happen, that's what we expect to happen. So we're trying to see if what we observed matched what we expected. And those are going to be two important words we're going to use because the formula uses those two values. So our hypothesized frequency distribution consists of expected frequencies. Hypothesized, expected. Empirical frequency distribution, the data we've collected, is observed frequencies. So we've got observed and expected. An important note here, and this is something that'll actually come back up when we're talking about ANOVA in a couple weeks, is chi-square does not tell us whether the observed frequency is different for the expected frequency for any particular category. Let's say we collect Ford, Chevy, and Toyota, and we get a significant chi-square. And we're hypothesizing that they're going to be distributed in a certain way. When we collect data, we observe cars going by, and we run the chi-square test, we get a significant chi-square. All that significant chi-square says is that there is a difference from the expected and the observed. So there's a difference present somewhere. At one of the categories at least is different than what we expected. It does not tell us what specific category is significantly different. To find that out, you do what's called post hoc tests. Now we're not going to do post hoc tests for chi-squared. I could teach you a few of them, and you do post hoc tests to figure out exactly what categories are different. So let's say you've got that Ford, Chevy, Toyota example. You can run and you get a significant result. You can run a post hoc to see if Ford significantly differed from what we expected, if Chevy significantly differed, and if Toyota. It could be all three of them differed. If you got a significant result, at least one of them differed, but it could be all 1, 2, or 3. And you do a post hoc again to figure out which ones differed. Like I said, I could do that, but I'm not, it's a bit beyond the scope of the class for post hocs for chi-squared. That being said, when we get to ANOVA, it's a very similar thing. ANOVA is a parametric test that looks at kind of the same thing as this. And in that, we will do a post hoc test. It will be part of what we'll learn, and it will be part of the last exam. So when we're doing chi-square tests, the hypotheses, the null hypothesis is basically indicating what we've already said, that the empirical distribution matches the hypothesized distribution, that observed equals expected. The alternate hypothesis is that the empirical distribution does not match the theoretical distribution. What you'll often see stated here is a at least one. So the null hypothesis will be that observed equals expected. The alternate hypothesis will be that at least one observed does not equal expected. And you'll see this also again when we do ANOVA. With chi-square tests, they are always non-directional, at least for the purposes of this. There are other types of chi-square tests that you can do that are way beyond the scope of this class, that are advanced statistics that will become directional. But for the purposes of everything we're going to do in here and all the basic chi-square tests, they're always going to be non-directional. They're always going to be two-tailed. We're going to use chi-square critical charts. I've got it on the next slide. We'll talk about it briefly a little bit more on the next slide. Chi-square tests, as I said, are two-tailed, so there's only going to be one critical value, and it's going to be based on alpha in degrees of freedom. Like I said, there's ways to get around the two-tailed, but that's way more than what we're going to cover. Figure they're two-tailed. It's always two-tailed. It's always one chart. And the critical value is going to be based on alpha in degrees of freedom. And one thing you'll find for degrees of freedom for chi-squared is that they tend to be very small. For instance, most of the examples we're going to use, the largest chi-square degree of freedom you'll find is 4. And that's a bit large. You're typically going to have 1 to 2 for your degrees of freedom. But we'll come back to that when we get to examples. The chi-square observed and chi-square critical are always going to be positive. And if our observed is greater than or equal to our critical, we reject HO just like normal. I'm going to throw a wrench into that as soon as we get to the other non-parametric tests. But just like the t-tests and z-tests we've done so far, if your observed is greater than or equal to your critical, you reject HO. If not, you fail to reject. Here's that t-critical chart. For the most part, we are going to be using this column right here because we're looking at an alpha of 0.05. You see this has got some weird alphas, 0.99, 0.975. That's because it's possible to do a left tail as well. So a chi-square distribution is actually skewed to the right and it's shaped like this. So when we're looking at 0.05, we are looking at the 0.05 over here. If you did 0.99, it would be all the way over here. But we're going to be doing 0.05. It's, as I said, chi-square distribution is a skewed right distribution. And for this, the important numbers are going to be what's up here. If I can get this to right. Because for the purposes of this class, we're never going to get to a degree of freedom over 5. It is possible to get to a degree, to have a degree of freedom of 9 and 6, but we're really just going to have 1, 2, 3, and 4 are going to be the 4 that we're going to do. We won't even get to 5 in here. And most of the time it's actually going to be 2. So this 5.991 that you see here, I cannot get my marker to right today, but 5.991 is going to be the most common one we're going to do, as you'll see from our examples. So this is the chi-square goodness of fit test. The chi-square goodness of fit test is the first one we're going to talk about here of the two tests. The two chi-square tests are very similar in how they work. Everything we've been talking about up to this point is that way. The first one we're going to talk about is chi-square goodness of fit. So chi-square goodness of fit test is when we have one variable and multiple categories of that variable. So our one variable is, in the example I've been using so far, is cars. And we have multiple categories of the cars. We have Ford, Chevy, and Toyota. From here on out, K is always going to represent the number of categories. So if we look at that, what we were just talking about, Ford, Chevy, Toyota, K is going to be equal to 3. The number of categories is 3. our degrees of freedom is equal to k minus 1. So if we've got 3 categories, our degrees of freedom is 2. Hence why, as I said, we're going to typically have that 2 as our degrees of freedom. If I had 4 categories, Ford, Chevy, Toyota, and let's say Audi, then we've got k of 4, so 4 minus 1 is 3. And you could have 10 categories, 20 categories, 30 categories. That's where you get those bigger degrees of freedom. But for our examples in here, we're going to typically have 3 to 4 categories at most. Now, this formula you see here, it's actually pretty simple. What this is saying is you're going to have the sum of all observed minus expected squared divided by expected. So you're going to have, and we'll see this in the columns coming up, but it's typical to write it. You've got an observed column, an expected column, observed minus expected squared, and then finally observed minus expected squared divided by expected. And then you sum up that column, and this is your chi-square, is the sum of your final column here. So example, just real quick, if we had, let's say we counted cars going by, and we expected them, we expect there to be 10 of each. We count 30 cars, we expect there to be 10 Ford, Chevy, and Toyota. We expect 10 of each, but we count 5 Ford, 15 Chevy, and 10 Toyota. Well, we've got our observed and expected now. Observed minus expected, this would be -5, this would be 5, this would be 0. We square each of these, so this one's 25, 25, and 0. We divide then the observed minus the expected squared divided by the expected again, back here. So 25 divided by 10 is 2.5, 2.5, and 0. So our chi-square value is 5. Pretty easy to do when you've got easy numbers like that. And it's a pretty simple test to do. Now on the next slide, I'm going to start talking about expected, because the hardest part of chi-square isn't the formula that we just did. The hardest part of chi-squared is calculating the expected values. Sometimes you'll be given expected, but quite often the expected you're given might be a frequency, not a frequency, might be it'd be a frequency, it'd be an absolute frequency. Since it's not a relative frequency, if you're observed, if the data set that you collected for your observed has a different n than the expected, then the observed and expecteds are going to be off, and you need to adjust them. What do I mean by that? Let me get to the next slide and we'll talk about that a little bit more, because there are multiple different ways to calculate expected. So, when we look at this, when we're calculating expected frequencies, and as I said, the hardest part of doing chi-square tests is calculating expected. When we get to the test of independence, it's a bit easier, but for this, let's look at 3 different methods for calculating expected. So, in general, all categories are going to be expected to be equal. If all categories are equal, expected to be equal. If all categories are expected to be equal, then the expected for each category is going to be probability of that category times n. N being the n from the sample. And that should even be a lowercase n, but n being from sample, so the sample n. The p, the probability, is going to be equal to 1 divided by k, where k is the number of categories. So if there's 3 categories, then probability would be equal to 1 divided by 3, which is equal to 0.3333. But then to get the expected, we need to multiply that 0.3333 times our n for each category. When the categories are expected to be equal, the expected is going to be the same for each category. So you just need to do this once. 0.3333 on my example on the previous slide, n equaled 30, because we counted 30 cars going by. So n equaled 30, so you'd multiply 0.333 times 30. So in this case, expected equals 30 times 0.3333, or expected equaled 10. So if you remember from the previous slide, we had an expected of 10 for each category. So when all categories are expected to be equal, this is an easy one. The expected equals the probability times n being from the sample, probability being equal to 1 divided by k. This is the easiest way to calculate expected. But this only works when categories are expected to be equal. Sometimes categories are not expected to be equal. So when categories are not expected to be equal, you're given different probabilities for each category. Sometimes you are, sometimes you're not. Sometimes you're given frequencies, sometimes you're given probabilities. But if the categories are not expected to be equal, but you've been given probabilities, then the expected for each category, calculated separately, equals probability times n. Again, n is from our sample size. But this needs to be calculated separately for each category. So let's say I thought that 40% would be Ford, 30% would be Chevy, and 30% would be Toyota. Well, then you've got a different probability for each one, 0.4 for Ford, 0.3 for Chevy, 0.3 for Toyota, and you multiply each of those by n. 0.4 times 30 would be 12, 0.3 times 30 would be 9, so it would have been, the expected would have been 12, 9, and 9, rather than 10, 10, and 10. That is, if you're given probabilities for each category. However, that's not often the case. What is often the case is you're not given different probabilities. What you're instead given is basically a hypothesized frequency. And in this, you still need to use the expected equals probability times n for each category. However, you need to calculate the probability for each category, whereas the probability for each category is the hypothesized value for that category divided by the total number in the hypothesized distribution. This n is the big N because this is in the hypothesized distribution. So let's say I was comparing, again, Ford, Chevy, and Toyota, but I was comparing it in Detroit to Windsor. And in Windsor, I calculated 100 cars going by, and I counted 40 Ford, I counted 30 Chevy, and I counted 30 Toyota. Now I am comparing a U.S. sample, a Detroit sample, to that. I've got the hypothesis that it's the values differ in Detroit than they do from Windsor. Though now I'm not given probabilities for Windsor, I was given frequencies for a sample calculated in Windsor. So now I'm going to have to use this formula here, this probability equals x divided by n, for each category. So the probability for Ford is, first we need to calculate out our n here, and this is again the n from the hypothesized distribution, not from the sample. Our n here is 100. So for this, for Ford, we need to do 40 divided by 100 to get the probability. Chevy's 30 divided by 100, and Toyota's 30 divided by 100. And then here you get 0.4, 0.3, and 0.3. So now you have probabilities. Now you apply these probabilities again, going back in the same way you did in method 1 and method 2. So if you're given, if all categories are equal, it's easy. You just do one time you do probability times n from the sample, where probability is 1 divided by k. And you apply that expected to all categories. If all categories are not expected to be equal and you're given probabilities, you need to calculate that instead of once, you need to calculate it for each expected category. And if you're not given probabilities, but you're given a hypothesized distribution, you need to calculate the probability and then apply it for each category. So example here, just one more example. We've got a hypothesized distribution of A equals 10, B equals 20, C equals 30, and D equals 40. N equals 100 here. I try and keep my numbers easy. We need to calculate probabilities for each one. So probability for A is 0.1, B is 0.2, C is 0.3, D is 0.4. Then we need to get expected for each one by multiplying that probability times the n of the sample. So a sample is collected where n equals 400. So 1 times 400, 0.1 times 400 is 40, all the way up to 0.4 times 400 is 160. If you sum up all of the expected, you notice that it equals the n from the sample. That's a important way to double check yourself. All of your expected should add up. Sometimes rounding errors will get you slightly off, but all of your expected should add up to total your n from your sample. So let's look at an example. In this example, we have we're interested in determining if teenagers prefer a particular type of movie. We ask 800 teenagers which type of movie they prefer, comedy, action, or suspense, and the following data is obtained. These are observed frequencies. These are going to be our observed frequencies. 400 for comedy, 300 for action, 100 for suspense. We are trying to see if there is a difference. So in this case, we don't need to be given expected frequencies or probabilities because all categories are expected to be equal. If we're trying to see if there's a difference, the null hypothesis is that all categories are equal. So null hypothesis is that there is no preference for movie type, that all categories are the same. The alternative hypothesis is there is a preference, and that at least one category is not the same. You see those words now, at least one, used here in the context of example. The data is nominal, and we have one sample, so we're doing a chi-square goodness of fit test. It's non-directional because all chi-square are non-directional. Our alpha equals 0.05, our n equals 800. You got that from the previous one if you looked at 800 total. Our degrees of freedom is going to be categories minus 1. There was 3 categories, so 3 minus 1 is 2. And our chi-square observed is going to be, again, the sum of observed minus expected squared divided by expected. As far as determining the expected frequencies, again, all categories are expected to be equal. So expected is going to be probability times n for all categories, where, again, probability is 1 divided by k. Our n is 800. So we need to do 1 divided by k, 0.3333, times 800, 266.6667. For all categories. The expected is going to be the same for all categories, and it's going to be 266.67. You notice I put it out to 4 decimal places here because I prefer before you get to the final step, it reduces rounding errors. But if you did it just to 2 decimal places here, I wouldn't mark you wrong. I prefer you go to 4 decimal places and tell the final answer. So let's look at that, how that would be charted out. There is an extra column that skipped here that would just be observed minus expected squared, but so observed minus expected squared would have been there, but that's fine. We're still getting the relevant information. So we got each observed value. We've got each expected value. You see they're all the same from the previous slide for expected. You take observed minus expected, you square it, you divide back by the expected for that column, and you sum those and you get your chi-square value, which is a very large number, 174.9978. That's because our n is 800. It's very easy to get a significant chi-squared, especially when you've got much larger sample sizes. So our chi-squared observed is 174.998, or just, you could put 175.00 if you were rounding to 2 decimal places. Our chi-square critical from the chi-square tables, that 5.991 I said would come back quite often. Since 174 is greater than 5.991, we reject HO. Given an alpha of 0.05 and a chi-square with degrees of freedom of 2 equals 174.998, reject HO, and conclude that there is statistically significant evidence for a movie preference. Very simple, right? Again, the hardest part is calculating out the expected. Okay, so the other chi-square test we're going to do is the chi-square test of independence. So whereas the goodness of fit is when you have one variable with multiple categories, the chi-square test of independence is when you have two variables that each have multiple categories. So it's when you've got two categorical variables. And these two categorical variables, we are trying to see if they are independent or if they're related. So this would be the equivalent of a correlational analysis that we would do in a parametric way, but we're instead doing it in a non-parametric way because the variables are categorical, not interval or ratio. The null hypothesis is basically just going to state that the two variables are independent, and the alternate hypothesis is going to state that they're related. And the probabilities for each cell are obtained under the assumption that the null hypothesis is true. So when we basically what this is saying is when we calculate expected frequencies, we are going to calculate expected frequencies in such a way that we are assuming that the null is true in order to see if our observed values match those null expected frequencies. The formula is essentially the same. You see two sum symbols here. Why is there two sum symbols here? It's basically just saying you do this for all cells. You do this for all cells in all rows and columns. Why? What do I mean by that? Because you're going to have variable 1, let's do variable 2, and you've got category 1, category 2, category 3, category 1, category 2, category 3. You're going to have all these different cells that we're going to deal with. So you've got rows and columns. But basically what this means is why there's two sum symbols is you're going to do the observed minus expected squared divided by expected for every single cell. I'm not going to write it on all of them, but you're going to do the observed minus expected for every cell, observed minus expected squared divided by expected for every cell. Then you're going to sum all cells. Sum the value you get from all cells. And that is your chi-square observed value. Our observed frequency is going to be from the data. Again, easy, that's just what you're given. The expected frequency you have to calculate, but the expected frequency gets a little bit easier here in that you've got total here, total here. You're going to have a total value of total of K1, total of K1 here too, because I did two K1s. But you're going to take, to get the expected, you're going to take that row total, multiply by the column total down here, and divide by n. So down here is going to be your n. Divide by your n total to get the expected. So the expected for it's going to be row total times column total divided by n. So in that way you are getting a expected frequency. Let me give an example of that. So the example here. Our example is a researcher wants to know if voter preference for candidates running for a political office is related to voter political party affiliation. The researcher surveyed 100 voters, asked them for their political party affiliation, Democrat, Republican, or Independent, and which candidate they preferred, A, B, or C. Conduct an appropriate statistical test using an alpha of 0.05. So our null and alternative hypothesis, the null is just that preference is independent of party affiliation. So candidate preference. So the null is that they are independent. The alternate hypothesis is that preference is related to political party affiliation. The alternate hypothesis is that our two variables are related. Our data is nominal. So we're going to be doing, and we've got two variables, so we're going to be doing a chi-square test of independence. They're non-directional because all chi-square tests are non-directional. Our alpha is equal to 0.05. Our degrees of freedom here, and I had it on the previous slide, but I didn't talk about it then, is going to be equal to the number of rows we have, minus 1, times the number of columns we have, minus 1. In this case, we've got 3 rows because we've got 3 political parties. We've got 3 columns. We've got 3 political candidates. So 3 minus 1 times 3 minus 1 is 4. This will be a typical one. You'll see here, actually, the common ones. So if you've got a 3 by 3, degrees of freedom is going to be 4. If you've got a 3 by 2, degrees of freedom is going to be 2. And if you've got a 2 by 2, your degrees of freedom is going to be 1. There is a correction factor if your degrees of freedom is 1, but I'm going to say this now and I'm going to say it later. You do not need to do the correction factor if it comes up on the homework or the exam. There's just, the correction factor is something you're supposed to do. It just adds one extra layer of complexity. If I give you a 2 by 2 on the homework or the exam, you do not need to do the correction factor. You can just use the degrees of freedom of 1. So here we have our observed frequencies. So our observed frequencies, 20 individuals who claim to be Democrat would vote for candidate A. 20 who claim to be Democrat would vote for candidate B, and 10 would vote for candidate C. Let's fill out our totals here, if I can get my marker right. And I can actually do math. Just make sure that adds up. Yep, it does. So, if you look here, 50 plus 30 plus 20 equals 100. 45 plus 27 plus 28 also equals 100. So we've got our row totals and our column totals. Now, I'm not going to go into all of them on this one, but to get expected, and I'm going to write observed here, because these are observed. Next to that, you can put your expected values. So we've got our observed and our expected values. The expected value for Democrat that voted for candidate A is going to be equal to 50, that's the row total, times 45, that's the column total, divided by n, which is 100. And you actually get a value there of 22.5, which you'll see on the next slide. But that's how you would calculate the expected. And you would do that for every single column. Let's look at Republican and B. It would be row total, which is 30, column total, which is 27, and N, which is 100. And you actually get 8.1 there. And you could do this for independent and C, 20 times 28 divided by 100. So that's how you would calculate out each of the expected. Let's look at that on the next slide. So this is with all of the expected. So you've got observed and expected, observed and expected, observed and expected. Now the chi-square, again, going back, if you remember, chi-square, it's going to be equal to the sum of the observed minus the expected squared divided by expected. So for each and every cell we've got here, we need to do observed minus expected squared divided by expected. And once you do that, you sum all of those to get to your chi-square value. Let's actually look at that on the next slide. So here I created a chart. You've got the cell is going to be, for this first one, voted for candidate A, Democrat. Voted for candidate A, Republican. Voted for candidate A, Independent. All 9 cells are here. Here you've got their observed. Here you've got their expected. You just take your observed minus your expected. You square it. You divide that value by the expected for that. So again, this one here is equal to 20 minus 22.5 divided by, and that squared, divided by 22.5. This one down here is 13 minus 5.6. That value squared divided by 5.6. And you do that for every cell. You sum them together, and you get your chi-square value down here. So when you sum them all, you get 23.94. Then you need to get the chi-square critical value from the chart. Our degrees of freedom was 4. Our alpha is 0.05. You notice that I only gave you one chart. There's a different chart. There would be different charts, but for the purposes in here, just go with that chart. Alpha is 0.05. You have to find alpha. Degrees of freedom is 4. So our chi-square critical is 9.488. 23.94 is greater than 9.488, so we reject HO and conclude that there's statistically significant evidence to indicate that candidate preference is related to political party affiliation. Remember, the alternate here is that they're related. When you're doing chi-square tests, there is actually assumptions that must be met. Like I said, even non-parametric tests have assumptions. If those are violated, you'd go to another test, another non-parametric test that's of lower level. So one is the observations must be independent. As I said, this is pretty much a universal of statistics test, because if the observations are not independent, there is bias within the test. And this doesn't mean that the categories are independent. Don't get this confused with the test of independence. This means that the observations, individual people that are polled, are independent, and that is sampling methods. The categories must be mutually exclusive. You can't have overlap, and your n's must be sufficiently large. So for a chi-square goodness of fit test, and even the test of independence, expected frequencies should always be at least 5 for all categories. For the purposes of in here, don't worry about that one if that comes up, but that is one of the assumptions. If your any of your expected frequencies are less than 5, you need to do a different test. You can't do the chi-square test. And I said if your degrees of freedom equals 1, there is a correction factor to do. As I said before, and it even says it on this slide, don't worry about using this in class. If your degrees of freedom equal 1 on the homework or the quiz, just do the test as normal. Don't do the correction. If you do the correction, I'm not going to mark you wrong. It's just more work for you to do because it's an extra step. As you see here, you have to do the observed minus the expected. You have to take the absolute value of that. Then you subtract 0.5 from each. Then you square it. Then you divide by expected. It's that extra step you just don't need to do because it's not something that's going to come up typically in the real world as something to worry about. Okay, now we are done with the chi-square test. Let's look at the two sample nonparametric tests that are very similar to the two independent samples and the paired samples t-tests. These two tests are going to basically be the equivalent tests when the parametric assumptions are violated. So when those parametric assumptions are violated, you do these tests. So first, let's start with the two sample test, the two independent sample tests, sorry. This is when you have an ordinal dependent variable or an interval ratio dependent variable with violated parametric assumptions. In that case, the dependent variable is treated as ordinal. It is a test that is essentially, and as you're going to see when we get to it, it is basically looking at it in a very similar way to the median. So it's used to determine if two distributions of scores differ in terms of location. Just like the parametric tests where we're looking at location, but we've got mean. We were looking at they differed in mean. In this, we're just looking at if they differ in location as a whole rather than just the means differing. So when the distributions are symmetrical, it's considered a test of differences between the medians. So as I said, we look at this almost like it's a test of the medians. We don't directly call it a test of the medians, but we can basically look at it in that way. It's a way we can think about it. Just like the independent samples t-test, the hypotheses can be directional or non-directional. So they're not specific like the chi-square test. It's specific to the hypotheses and whether the hypotheses are directional or not. So the Mann-Whitney U test is a interesting test, and it's actually a relatively simple test. And when we get to this and the Wilcoxon T, the sign rank test, there is there's a few things going on here that make it a little bit more complex, but these two tests are actually pretty easy. There's going to be two values we're going to calculate for the Mann-Whitney U test. It's going to be U1 and U2, and our U observed statistic is going to be the smaller of U1 and U2. So you're going to calculate out both U1 and U2, but your test statistic, your observed, is going to be the smaller of them. So once you've calculated out the two, you just discard the one that's greater. The steps in doing this: first, you are going to take all scores in your distribution in both sets. So you've got two independent samples. Let's say we were using that example like hugs given from the quiz, and we've got father's hugs given and mother's hugs given, and we've got number of hugs given. We are going to rank all of the scores from the highest to lowest, ignoring what group they're in. So we are going to, so this is all scores, and that's very important. You're ranking all scores irrespective of what group they're in. It doesn't matter what group they're in. It doesn't matter if it was fathers or mothers. You rank all of them. So if the lowest amount of hugs given was 1, and that was a father, they would get a rank of 1 because you're ranking them from lowest to highest. If the next lowest amount of hugs was 3, and that was a mother giving 3 hugs, that would get a rank of 2. So you rank all scores from lowest to highest. Tied scores receive average ranks. What does that mean? If you've got a husband, two different husbands that each gave 1 hug, they would each get the tied ranks. How does the tied ranks, average ranks work? Well, you're using up ranks 1 and 2. It's the first two people, you're using up ranks 1 and 2. You'd take an average of the two of those, so they would each get a rank of 1.5. So average ranks are used in a very similar way to when we were calculating the median. You use average. When you were calculating the quartiles, you use an average of the different ones. Well, for here, you're doing average ranks. Then, separately for each group, so in our example, husbands and wives, you compute the sum of the ranks of all individuals in that group. So you calculate up a sum of husbands' ranks and a sum of wives' ranks, and then you calculate out U1 and U2 by doing N1 times N2 plus N1 times N1 plus 1 divided by 2 minus the ranks for that group. So if group 1 was husbands, it would be minus the ranks for group 1. You do the same thing for group 2, except now it's N2 times N2 plus 1 for the middle part, and then you subtract ranks for the second group, ranks for wives here. Important to know, if your N1 and N2 are equal, you don't have to do everything before the ranks more than once. You just need to do it once because it's going to be the same either way if your N's are equal. Our Mann-Whitney U critical table is going to be based on an N1 and N2 and one-tailed versus two-tailed. So just like with the independent samples test, you need an N1 and an N2 to figure out, well, the independent samples, you got a degrees of freedom from the two of those. For this test, you're actually going to need both of those as separate values. Your U observed and your U critical are always going to be positive, and here's where I throw you a curveball. This annoys me to no end. I can't tell you how much this annoys me, but the way the initial people who made this test did it is it's opposite of every test we've done so far. In that, if your observed is less than or equal to your critical, you reject HO. Otherwise, you fail to reject HO. So, important note, this is opposite of every test we've done to this point. Every test we've done to this point, if your observed was greater than your critical, we rejected. Now for this test and the Wilcoxon T that we'll do next, if your observed is less than your critical, you reject HO. I can tell you that it's absurd because there is ways to do it. If instead of using U1, the U observed that's the greater of the two you observed, if you remember, you use you use the smaller of the two U observed, so your U observed becomes the smaller of the two U values you get. So if U1 is smaller, you use that as your U observed. If instead of using the smaller, we use the larger and the table corresponded to that, you could do this just like the T tables where observed being greater than. Like I said, it's absurd, but I'm making a big deal out of it because it's something that I know it causes confusion. But for the Mann-Whitney U and the Wilcoxon T test, it's going to be the opposite of everything else in that if observed is less than or equal to critical, we reject rather than rejecting if it's greater than. Here is our Mann-Whitney U critical tables. I put two tables here. This is only for alpha 0.05. If you had other alpha values, you could use other critical tables. But this is for, on the right is going to be for one-tailed, on the left is going to be for two-tailed, non-directional. And you see here you've got your N1 and your N2. As you can see, your N's need to be relatively large for you to even do this test. For a directional test, you need N's of at least 4. For a non-directional test, you need it a little bit higher, up around 5, before you can really run it. Now that's fine, your N's should be higher than 4 or 5, but if I give you an example that's got an N1 of 8 and an N2 of 8, and you're doing a directional, then you'd use this right chart over here and just line up the 2 8s, and you get a value of 15, and that will be your critical value that your U observed has to be less than or equal to reject. Let's look at an example real quick, especially so you can see how these rankings work. So we want to know if there's a difference between males and females in general knowledge. 5 males and 5 females are randomly selected to give a 50-item general knowledge test. Scores below are the number of correct. Assume that the assumptions for the t-test are not met, so the parametric assumptions are violated. We are given our 10 values here. Conduct an appropriate test using an alpha of 0.05. So we're going to do the Mann-Whitney U test because we've got 2 independent samples. There's no pairing mechanism. It's still important here. There's no pairing mechanism, and the parametric assumptions are violated. Our null hypothesis is that male equals female. Our alternate hypothesis is that male is not equal to female. In general knowledge, you could put that there as well. We're doing a Mann-Whitney U test. It's two-tailed. Alpha equals 0.05, N1 equals 5, N2 equals 5. Degrees of freedom is not applicable because there is no degrees of freedom for the Mann-Whitney U test. Now here you see an example of what's going on with rankings and how the rankings work. You can see some of the tied rankings. Let's go through these. So you're ranking them from smallest to largest, irrespective of group. So you've got males, females. The lowest score on both groups is a 24 here, so it gets a rank of 1. The next lowest score is a 26, which applies to both groups. There's 2 different 26s. There's a 26 here, and there's a 26 here. So because we've got 2 26s, we need to average the ranks. There is 2, so we're taking rank 2 and rank 3. Because we've already used rank 1, the next 2 ranks are rank 2 and rank 3. You do 2 plus 3 divided by the number of tied ranks equals 2 equals 2.5 or equals 2.5. The number of tied ranks is 2. There were 2 ranks tied. The ranks that they would take up is 2 and 3, so they each get a 2.5. Let's say for a second you had 3 ranks tied instead. So alternate example. You had 3 scores of 26. You already had that 24 there, but you've got 3 scores of 26. So now you need to take the ranks they would take up. So you'd have rank 2, rank 3, and rank 4. Add all of them together and divide by the number of tied ranks, which in this case is 3. And you actually get a total of 3, so you'd give a 3 to each of those in this alternate example. I hope that makes sense. If you had 4 scores tied, you do 2 plus 3 plus 4 plus 5 divided by 4. If you already had like 4 ranks out there and then you got to 3 scores tied, then it would be the 5th rank, the 6th rank, and the 7th rank, so it'd be 5 plus 6 plus 7 divided by 3. Let's keep going through these. The next lowest score is a 29, so that gets a rank of 4. You notice that gets a rank of 4 because we've already used up 2 and 3. That's where that 2.5 came in for both of them. We've used up ranks 2 and 3. The next lowest rank is 4. The next lowest score is 31. It gets a 5. Next lowest score is a 36. We've got 2 36s though, so we average them. We're using up 6 and 7. There's 2 scores that are tied, so we get 6.5. Next lowest score is a 38, but we've used up rank 6 and 7, so it's going to be rank 8, then rank 9, then rank 10. Now, next thing you have to do is sum the ranks for each group. So you sum the ranks for each group. This group has a total of 23. This group has a total of 32. So our R1 and our R2, don't confuse this with our U values because we still have to calculate out our U values. This is our R, our summed ranks value. So from this, we need to now calculate the U's. Let's do that on the next slide. So U1 it's going to be equal to n1 times n2 plus n1 times n1 plus 1 divided by 2 minus ranks 1. Ranks 1 was 32. So we get if we add all of that up, we get 8. If we factor all of that out. I should point out that because n1 and n2 are equal, you don't necessarily have to calculate all of this again because it's the same as what you calculated up here. So you would just take the same thing, which that totals out to 40. 40 minus 23 becomes 17. Our U observed is the smaller of the two, so our U observed is 8 in this case. So step 5 is our U observed, it's the smaller of the two. Step 6 is our critical. Our critical is going to be the N1 of 5 and 2 of 5, and it's a non-directional. You go to that chart back on the Mann-Whitney U, and you get a critical value of 2. And again, it's opposite, so you need to be less than or equal to that. Because 8 is greater than 2, we fail to reject HO. So given an alpha of 0.05 and a U observed equals 8, fail to reject HO and conclude that there's insufficient evidence to indicate that males and females differ in terms of general knowledge. It is harder to reject HO in a non-parametric test than it is a parametric test. That is because these tests being non-parametric have to be more conservative to account for the non-parametric nature of the tests. So that is one thing that I will point out now that you'll see. Yes, you'll see non-parametric tests rejected, but it is harder to reject HO in a non-parametric test. All right, let's look at the last test. The last test is one of my favorite tests, and it's also very easy, pretty simple to do. So the Wilcoxon T is going to be the non-parametric test for paired samples. So in this case, when we've got two paired samples, just like we've got independent and paired samples t-tests. When we've got independent non-parametric, we do Mann-Whitney U. When we've got paired non-parametric, we do Wilcoxon T. So you need a logical pairing mechanism, but it's when the parametric assumptions are violated. And just like the Mann-Whitney U, it's used to determine if scores differ in location. So just like the paired samples parametric t-test, it's whenever you've got a logical pairing mechanism. Repeated measures, before, after, something like twins, couples, logical pairing mechanism. Just like with the paired samples t-test, the first thing you do is you obtain differences between the scores. So you subtract one score from the other. Then we are actually going to discard everything before that because we are just like the paired samples t-test does a one sample test on the differences. We are going to do a test on the differences. An important thing to do though is, and this is one of those things that's kind of weird, but any difference of 0, anytime we get a difference of 0, we completely drop it from the analysis and we reduce the n accordingly. So if we've got an n of 35 and 3 differences are equal to 0, we drop those 3 out entirely and our n now becomes 32. That is one of the issues with the Wilcoxon match pair sign rank test or the Wilcoxon t-test, is that any differences of 0 we just ignore. It's lost data. Now, why do we do that? Because it's just the nature of the non-parametric test that we're doing. And it's the nature of the test. It's the only way we can legitimately run the test. So, any differences of 0, we completely remove them from everything, including reducing the n's. We've obtained differences. Now we need to go one step farther. Next, we rank the absolute value of the differences from smallest to largest. This is important, the absolute value of the differences. We rank from smallest to largest. So if you've got a score of -5 and another score of 7 and another score of, let's say, -6 and 4. Let's rank these 4 values. These 4 values, we're going to rank them. Their ranks We're going to rank the absolute value of them. What's the lowest? The absolute value of the lowest is 4. We give a 1. What's the next lowest? It's 5, so 2. The next lowest is 6, so 3. The next lowest is 7, so 4. So we rank each of the absolute values of the differences. So we take the absolute value of each of the differences and rank those. Then we sum the ranks separately for positive differences and negative differences. So over here on the right, what we've got here are positive and negative. If we sum them together, our positive, we've got, so this is a positive. We could even put positives next to our things for the ones that are not negatives. So 4 and 7, if we look at the ranks, we've got a rank of 1 and a rank of 4. So we've got 5. And let's even add another one here. Let's do negative 22. Well, this is going to get a rank of 5. So now we add up the ranks for the negative values as well. We've got negative 5 is rank 2, negative 6 is rank 3, negative 22 is rank 5. We add those up together, we get 10. So our negative ranks is 10, our positive ranks is 5. The smaller of the two is our observed t. So the smaller of the two is 5. That's our observed t. There is actually no math to do in this one other than ranking them, doing the absolute values. That's one of the reasons I love this test, is there is no formula. We just did essentially everything you need to do. You obtain differences, you throw out all zeros, you rank the absolute value of the differences from smallest to largest, you sum the ranks separately for positive differences and negative differences, and then the smaller of the two is your t-statistic. So the only math you have to do is taking absolute values and summing the ranks. Nothing beyond that. Then we need to get the critical value for the t-statistic, which we'll have on the next chart. Critical values are based on n. Don't forget to drop zeros from the differences. So when you're obtaining your critical value, your n is lowered based on any zeros. And it's one-tailed versus two-tailed. And t observed and t critical are always positive. And just like the Mann-Whitney U, it's the opposite of everything we've done so far. And that is, if your observed is less than or equal to your critical, we reject HO. And again, just like I said, it's kind of absurd because we took the smaller of the two for our observed. If instead we took the larger of the two and they had made a different critical chart for that, they could have done it the same way. But they didn't, so you get to deal with the confusion of the Mann-Whitney U and Wilcoxon T having the opposite decision rules. Here is your critical chart. So you've got two-tailed and one-tailed. Just look at those two. So one-tailed 0.05 is right here. Two-tailed 0.05 is right here. So these are going to be the two columns that you're going to use for in here. Two-tailed 0.05 is that second column, the column here. One-tailed 0.05 is the column here. So those would be the two you'd use. You notice your ends have to be, your end has to be pretty large. Not pretty large, it just can't be too small. An n of 6 basically, you could do it with 5, but you've got to have all the ranks have to be in the other group. For a one-tailed and for two-tailed, you have to have an n of up to 7 as a minimum basically. So let's look at an example of that. The example is there a difference between National League and American League and the average number of bases stolen per team? The data that's going to be given on the next slide are the average number of bases stolen for each team per year over a period of 11 years. For the National League and American League, we're going to use alpha of 0.05, conduct an appropriate statistical test, and we're assuming that we've violated the parametric test assumptions. So our null hypothesis is that the National League equals the American League in number of bases stolen. The alternate hypothesis is then that there is a difference, that the National League is not equal to the American League in average number of bases stolen. We're doing a Wilcoxon t-test, and you notice again this is the big T, not the little t, because we've got paired samples and the parametric assumptions are violated. It is a two-tailed test because now we go back to our hypotheses. Our hypotheses are non-directional. Step 4, which I'll actually have in a couple slides, is going to be alpha of 0.05, but there's a reason I skipped step 4 at this point, and that is because we can't determine our n yet. To determine our n, we have to do differences first, because remember, we drop out any differences of 0. So let's look at these differences. So first we've got our National League here. We've got our American League here. Then we do the differences. And now we are no longer considered with everything going on over here. We just are looking at our differences here. Our differences are all that's important now. First, we are going to rank them, ignoring signs. So we've got the lowest, from lowest to highest. The lowest was 5 here, so that gets a 1. The next lowest is 7, because again, we're ranking the absolute value of the differences. So the -7, the 7 gets a 2, 10 gets a 3, 46 is the next lowest, but it's tied, so we do average ranks just like with the Mann-Whitney U. So we've got 4.5 to each of them. We've now used up 4 and 5, so we need to go to 6. The next lowest is 53, then 56, then 60, then 64, then 65, and you notice that we've got a 0 there, so we take that one out. Our n originally was 11, but our n is now going to be 10 because we have completely eliminated that line. We just completely throw it out. Now we need to take all of the negative values. So you see that the only two negative values were -7 and -53. So you take the ranks for those. That was rank 2 and 6. Sum those together, you get 8. Then you take all of the ranks, the positive ranks, we get a 47. The smaller of the two becomes the t observed, which is equal to 8. Okay, so finishing up with that problem, now we've got an alpha of 0.05. Degrees of freedom is not applicable. You don't have to put that again. But our n is 10 because one difference of 0 reduced it from 11 to 10. You don't need to write that one difference is 0. You just needed to, I've just put that there as a reminder. Our t observed is the smaller of the two sums of ranks, which was 8. Our t critical from the chart, so it's a two-tailed non-directional with an n of 10 and an alpha of 0.05, so our t critical is 8. 8 is less than or equal to 8, so we reject HO. Given an alpha of 0.05 and a t observed of 8, reject HO and conclude that National League teams steal significantly different amount of bases than American League teams. We can go look at it and see that National League were greater than American, so the National League steals significantly more bases on average than American League teams. So that's a Wilcoxon t-test. Very easy stuff, fun stuff. Like I said, this is one of my favorite tests. It's called the Wilcoxon T sign rank test. There's actually another test that if the assumptions that are for this test that I didn't show you are violated, you don't even do the sign rank test. You just do what's called the rank test, and in that one you don't rank, or not the rank test, the sign test. And in the sign test, you don't rank them, you just apply a positive or negative to each one and add up the number of positives and the number of negatives. Rather than ranking each of them, you just have the number of positive differences and the number of negative differences, which is a test that has even less work to do on it. But that's when the assumptions for this test are violated. All right, on this last slide, I'm not going to go through it that much, just real quick, just a kind of which test do you use? So we're doing a measure of location, typically mean, but not always mean. It could be median. If we're doing the mean or median, though, we're not doing correlation or anything else. We're doing that. We first ask how many samples do we have. If we have one sample, we do a one sample test. Then we need to know if the population variance is known. If yes, do a z-test. If no, do a t-test. If there are two samples instead of one, we need to first ask, are the samples paired? If they are, then we need to ask if the parametric assumptions are violated. If they are, we do that Wilcoxon t-test we just did. Otherwise, we do a paired simples t-test. Are the parametric assumptions violated? Next question is, it's not, for B is, are the samples paired? No. Then the question is, are the parametric assumptions violated? For that, then we would, if yes, we do a Mann-Whitney U. If no, we need to know if the population variance is known. If yes, we do a z-test. If no, we do a t-test. Okay, that lecture ended up a little bit long, but it is the chapter on nonparametric tests, and as I said, I could go on all day. I love nonparametric tests. They're a lot of fun. The chi-square tests are ones you'll actually possibly do, especially as you get into more advanced statistics like hierarchical linear modeling and things like that. When you get up to those levels, they pretty much are all using chi-square. Not the same chi-square test we did here, but the chi-square statistic. So they're using that as their decision statistic. All right, thanks. Come on back.